So these are nothing but, so when your ARM starts processing, so even if I want to increase the speed of my ARM processor, so I want to add some more extra components so that my system, my ARM microcontroller has to work efficiently. What they are going to improve? So whenever you are going to connect the standard components placed next to the ARM core, what they will improve? So they are going to mainly improve the performance, and it is going to manage the resources, and it is going to provide you the extra functionality. That means, so assume that you have built an embedded system which is performing some desired task, but you want some other task to be added for that particular embedded system. For how we are going to do that one? So by, if I want that one to be temporarily have to that particular functionality, so I cannot invest the whole thing to be there in to be inserted into your embedded system. For that one, what I will do, so I will add the extra functionality by the side. So if you add the extra functionality by the side, so what it will improve? So it will be improving your performance. So that means, so some more added processors can be added there. So it will be improving the performance. And if you add the storage for your then it is going to improve the storage. And it is not. It is also one of the resources which you want your arm to be make used. Okay, so what it is going to provide extra, so it is going to be designed to provide flexibility handling particular applications. That means depending upon the applications which you are going to use, so depending upon the applications, it will be flexible. Okay, so depending, my ARM processor is going to be inflexible with the different applications, the applications which they are going to build, so that will be flexible. So now, if we take the different ARM family, so if we take the ARM family, ARM 5 is, ARM 7 is there, ARM 9 is there, ARM 10 is there. So yesterday we discussed about the different stage of pipelining. Okay. So once you come with respect to the different stages of the pipelining, here what will happen is, uh, so, so if we take the ARM 3.7, so it is executing in three-stage pipelining. If we take ARM 9, it is executing in five-stage pipelining. If we take ARM 10, it is executing in six-stage pipelining. So now each ARM family is having the different extensions. Okay, so here, so the bare three extensions which your ARM core is going to have, there are three hardware extensions. So there are three hardware extensions, and uh, which are they? So which are around the core. So these three extensions which are there will make you improve your ARM core to be improved, having the improved performance. So this will be having the improved performance. Okay. So what are they? So the first one is your cache and tightly coupled memory. So you are going to have the extra function, extra component to be inserted, which is a cache and tightly coupled memory. Second is I will be having the memory management. So memory management will be there. And third, it will be having the coprocessor interface. That means with the existing processing of ARM, I'm going to introduce one more processor which is attached to the ARM core with the help of the interface. Okay, that is what the third coprocessor interface is going to tell. So next coming to what do you mean by cache and tightly coupled memory? So here, so as we have known that what is whenever your processor start executing its instruction, where the data it is going to see. So first it is going to look into the instruction. First it is going to look into the memory which is near to the processor. So the memory which is near to the processor is the cache. Okay, if you take the hierarchy of the memory, the processor first look into the cache. Okay, so now the cache is the block of fast memory, and it is between your what? It is between your main memory and the core. So main memory is nothing but your RAM, that is random access memory. So first the processor is going to look into the cache whether that particular instruction which I have to run is placed inside the cache or not. Okay, so if it is not there, so with the cache, the processor can, if that particular instruction is available on the cache itself, then what will happen? So your processor need not have to fetch the instruction from the main memory. So how the hierarchy goes is, first initially the instructions, whatever the memory, whatever the data or instruction which you are going to have, that will be stored in the secondary memory. When your processor first start executing, first the instruction or data which is there in the secondary memory has to go to the main memory, and from the main memory it has to bring to the cache memory, and from the cache memory, it will start executing on the processor. That is how the hierarchy will goes, right? So now, once it is happening, so with the cache, what will happen? The processor core can run for the majority of the time. So that means what? With the help of the core, what will happen? Whatever the data it requires, that will be stored. That particular instruction will be stored inside the RAM only, inside the cache only. So when it is placed inside the cache itself, so that particular processor core can run for majority of time. So without waiting for the data from the slow external memory. That means it will not wait for the data which has to be coming from the secondary memory. Because if it has to come from the secondary memory means what? First, the instruction or data has to be brought from secondary memory to the primary memory, which is nothing but your main memory. So from main memory it has to bring to the cache, then it has to execute. So the time will be more. The time taken to execute that particular instruction will take more time. So if you want to execute anything in less time, where that particular instruction or data should be stored, that particular instruction or data has to be stored in the cache only. So since the core has to be effective means what? All instructions to be there in the cache only. So if it is there in the cache only, what it means? It is your processor core is not waiting for the much of the time for the instruction to come from the second memory. So it is not having any wait time. Okay, so that is what it means. So now ARM processor is going to have the two forms of cache. That is okay. So that is one cache which is with respect to the one Neumann style cores. So in another type, it is called as hardware architecture. So one is your one Neumann style um, tightly coupled memory. Other is your hardware architecture with tight coupled memory. Now, if we take the one Neumann style, so one Neumann architecture, what it is going to have. So here in this type, so your execution, your instruction and data will share the same bus. If I start talking in the normal definition of your one Neumann architecture, so your instruction and data will be shared on the same bus. Similarly, here it is going to combine both data and instruction into a single unified cache. That means single cache is going to hold both the instruction as well as the data which that particular program has to utilize it. So if it is memory means what? That particular memory is going to have both instruction as well as the data. So next is our hardware style. So in a hardware style, what will happen? In hardware, it is going to have the separate instruction and data. Okay, it's going to have the separate cache for data and instruction. So you have to keep in your mind that ARM is going to have two forms of cache. One will be in the one Neumann style, other will be in the hardware style. So if we take the one Neumann style, that that particular cache is a unified cache. Unified cache, it comes into the mind is what? Both your instruction and data in the same cache. The cache is going to store both instruction as well as the data. So if you take the hardware style, hardware architecture is nothing but what? Your data and instruction are separate. That means the separate cache will be maintained for data also and for instruction also. So that's what your hardware style tells about. So if you take the simplified diagram of one Neumann architecture with cache, you can see it here. ARM core is there. So in the ARM core, so you are going to have the unified cache here. So with the help of the ARM core, it is going to access the data which is stored in the ARM cache. Okay, so that is unified cache. So unified cache is nothing but what? Your data and instruction both will be executing from this particular memory only. So your cache, if you take this cache is also nothing but the memory, where it will hold what? Both instruction as well as the data. So next, your ARM core, if you take the normal block diagram of your ARM data flow model, so ARM core, then it is going to have the logic and control unit. So how the logic and control unit and the memory are connected? Your logic and control unit and main memory is connected through the ARMBA bus interface unit. Okay. So what do you mean by ARMBA? So ARMBA stands for what? Advanced Microcontroller Bus Architecture. So that we have already discussed. So if you take the ARMBA is nothing but Advanced Microcontroller Bus Architecture. So this is the interface where it is going to have. So and how it is going to interact, this interface, how it is going, this logic control, the ARM core is going to interact with the main memory. Your ARM core is going to interact with the memory with the help of the on-chip AMBA bus. On-chip means what? On-chip AMBA bus. On-chip means what? You are going to have the IC. Inside that particular IC itself, this particular bus is residing. Okay. So AMBA stands for Advanced Microcontroller Bus Architecture. Okay. So now once it is going to have the AMBA bus, that is going to send to the my memory. So initially when your program, when you first start executing the program, where the core has to start, the core has to start from here, and it is going to check whether the instruction or data there in the unified cache. If the data and instruction are not there in the unified cache, next it will request the logic and control unit to perform the logical operation. Since there is no instruction to perform it, it is not going to perform any logic and control operation. Next, through the AMBA bus interface, what it is going to fetch? It is going to fetch the instruction which has to be executed from the main memory. So from the main memory, it is going to fetch the instruction or data which is required for that particular ARM core, and through the bus, it is going to store it in the unified cache. Either it may be instruction or it may be a data. So once the data and the instruction, once your data and instruction are stored in the unified cache, what will happen? Your ARM core is going to execute the data and instruction which is placed in the unified cache itself. That means your ARM core need not have to wait till the data or instruction is coming from the main memory. Okay, so that is how your one Neumann architecture style of tightly coupled memory is going to work. Okay, so next when it comes to the Harvard architecture, so you can see it here in the ARM architecture. What will happen? It is having the separate data tightly coupled memory and separate instruction tightly coupled memory. That means this particular cache which is going to have, it is going to store only the instruction. Your instruction tightly coupled memory, what it is going to hold? It is going to hold only the instruction. So if we take the data tightly coupled memory, this particular memory is going to hold only the data. So this particular memory is going to hold only the data tightly coupled memory. So now when you start ARM core start executing, what will happen? First, it will check with the data tightly coupled memory and instruction tightly coupled memory with respect to the instruction or data. So if ARM core is executing the instruction, it will check that whether that particular instruction is there in the instruction or not. Okay. So now once it is there in the instruction, okay, for example, ARM core is going to execute some add instruction. So first it will look into the add operation which is there in instruction tightly coupled memory or not. If it is not there, what it will do? It will send the request to main memory through the instruction bus. So it is going to have the separate bus here. You can take it here. So it is going to have separate instruction bus as well as the data bus. So once it is sending the request to instruction to be executed through the AMBA bus interface, it will, in the AMBA bus interface, it is going to support both data and instruction. So next it comes here, it will place a request to the main memory to it will ask the instruction which has to be executed, which is stored in the main memory. Now, the main memory will send the instruction which has to be executed. So once it comes and executed, so once it is going to execute here, now the same instruction will be stored in your instruction tightly memory. The same instruction is going to store in the instruction tightly coupled memory. Now, whatever the recently executed instruction is there, so that will be stored in instruction tightly coupled memory. So when it is executing it, from the memory, it will come into the ARM core and it will be stored in the tightly coupled memory. But what is the advantage of having your instruction tightly coupled memory? So how that particular instructions are stored in instruction tightly coupled memory is in your embedded system. So always your embedded system has to work for 24/7. If we take any embedded systems which is in real time, so those real time systems has to work for 24/7. When it is working for 24/7, what will happen? The very first access will be from the main memory. The very first access will be from the main memory. But after first access, where that particular instruction will be stored, this instruction will be stored in instruction memory. So next, the ARM core is going to look into the instruction memory only first. In instruction tightly coupled memory only. So if any instruction has to be executed, if that particular instruction is not there in instruction tightly coupled memory, then only it will going to look for the main memory. That is how the flow is going to work. Okay. If that particular instruction is not there in the main memory, next it is going to look into the secondary memory. It is like that. Hierarchy will go like that. So if your data or instruction are say stored in the separate access, a separate cache with respect to data cache of data tightly coupled memory and your instruction tightly coupled memory for instruction. So the performance will be improved further since you are since you are storing your instruction and data separately as a separate cache. Okay, so you are storing your data and instruction in the separate cache. Okay, so that is what the difference. That is that is one thing which you have to know about your cache. Okay, so that is with respect to the cache tightly coupled memory. Okay, so any doubt with respect to this one? Anybody is having any doubt? Anybody is having any doubt with respect to the core extension of cache and tightly coupled memory? Anybody having any doubt? You have to speak it out. You have to speak. If you're not speaking, how come we come to know that whether you people are listening or not? Okay. So now, so next is, so this is also a typical, the same diagram which is there in a different form. So next, when you are going with the cache memories, there what will happen? The time taken for loading and storing instructions or data must be predictable. That means what? So whenever you want to access, as I told in the beginning only, so when your ARM processor is not going to make use, not going to operate on memory only. So if it has to if it has to work, the ARM instruction has to work means what? First, the data or instruction has to be brought from the memory to the register. Then only you can work on the register. So for that one, what will happen? So you are going to first any program has to run means what? With respect to memory, you compulsory two instructions will be there. What are the two instructions? One is store instruction, other is load instruction. Your load instruction, what it will do? The load instruction is going to load the data which is stored in the memory to the register. So it is going to load the data from the memory to the register. So next comes the store. What the store instruction is going to do? The store instruction is going to perform the operation where after obtaining the result, the data will be moved from the register to the memory. So now these two instructions are compulsorily has to be done. First, bringing the data or instruction from the memory to the processor register, or sending the data from the register to the memory. Now, whenever you want to performance to be taken as consideration, if I want to have the more performance, then what I should have? Then I should have my time to be predictable. So the data, whatever the loading and storing instructions are there, so that that particular timing should be predictable. That means within this particular period of time only, it has to get the data from the memory, and it has to load the store the data from the register to the memory. So it should be predictable. That means within this particular time, that particular process will be completed. So how this will be achieved? This is going to be achieved using the form of memory called tightly coupled memory. Okay. So how this will be achieved? So this will be formed by the memory called tightly coupled memory. So your TCM is nothing but what? So your TCM is nothing but tightly coupled memory. So it is also referred as TCM now here. So in the tightly coupled memory is nothing but your fast RAM. So since already you know from the basics of your computer organization, so compared to your DRAM and SRAM, your SRAM is faster. Okay. So since the SRAM is faster, so TCM is nothing but what? TCM is a fast SRAM. But this particular fast SRAM, where it is located, that will be located near to the core. That is, it will be located close to the core. And since it is located close to the core, what it guarantees? So it is going to guarantee the clock cycles required to fetch instructions or data. So whenever you want to execute some program, means what? First, it has your program will be having a number of instruction. When it is having the number of instruction, one by one instruction it has to be fetched and it has to start executing. So who is going to locate which instruction has to be executed next? Your program counter. Now, when this sequence of process are going, what it has to guarantee? It has to guarantee that how many clock cycles are required to fetch the instruction or to fetch the data. So that is what your tightly coupled memory is going to do. So now, next coming to the memory management. Anybody having any doubt? Anybody having any doubt? Okay. Okay. So next coming to the memory management. So if we take with respect to the memory management, so here, here when you are going to have the ARM hardware, so ARM hardware is going to support you the three different types of memory management hardware. So our core has three different types of memory management hardware. So what are the three different memory management hardware you are going to have? One is it doesn't have no extensions, providing no protection. So it doesn't have any extensions and it is not able to provide the protection also. So other core you are going to have, other type of memory management you are going to have is MPU. So it stands for memory protection unit. So in the memory protection unit which is there, that will provide you the limited protection. That is going to provide you the limited protection. So third one is memory management unit. So the memory management unit, it is similar to the memory management unit. What it is going to provide is, it is going to provide you the full protection. A memory management unit is going to provide you the full protection. So now, whenever you are going to have the non-protected memory, so in the first type, when you are going to have the non-protected memory, so it is going to be fixed and provides limited flexibility. So your non-protected memory is fixed and it is going to provide you very little flexibility. So where this particular type of memory is used. So when you are going to have the little flexibility and you are going to have the limited protection, since we are providing the protection, I cannot go for the this particular type of memory where the time where you are going to have the hard real-time systems. So when you talk about the hard real-time systems, what will happen? There the time bound is important. So it has to guarantee the response time. Okay. So that means it has to meet the deadline. That means whatever the operation it has to do with that, it has to respond within this particular time period of time. That if you take the anti-braking system of your vehicle. So if you take the anti-braking system of the vehicle, whatever the new braking system is coming into the market is what? So whenever it is going to by MES, when you are traveling in a vehicle, what will happen? Some person may enter into the road suddenly. So now you don't have the control of that one. So at that time, what it has to happen? So your vehicle itself has to design in such a way that it has to protect itself. That means that particular embedded system work immediately. That means within that period of time, it has to apply the brake by itself and it has to stop the car. And the countermeasure it has to take. So that is another one is your airbag. So airbag itself, right? Whenever the accident is going to occur, the airbag has to open immediately. Okay, within some deadline, within some period of time only, that particular airbag has to open it. So if within that particular period of time, if the airbag is not opening, what it happens? So you are going to have some accident and injuries may occur for the human being. Okay. So this is one typical example where your real-time embedded system are used. So that is in airbag in your car also. That is one of the example for your end. So but when you are using this, when you are going to have this type of embedded systems, you cannot use the non-protected memory mode. Okay, so you are going to have the that is first one, no extensions. That means it doesn't have any protection. So these type of memories going to provide you the little flexibility, and we are not able to use this particular uh, type of memory where you are going, where your responses to be proper, or it should be precise. Your response should be precise. That means within this particular period of time, that particular event has to occur. So if this particular event is not occurring within that particular stipulated period of time, so more dangerous events are going to occur. So this is one typical example is your airbag in your car. Okay. So now if you take the non-protected memory, where it doesn't have more flexibility, it is going to provide you the less flexibility. So where it is going to be used? So it is mainly used in normal simple embedded systems. So simple embedded systems it is going to use, and it doesn't require no production from different applications. Okay. So it is going to be normally used for small and simple embedded systems where it does not require no production from other applications. Okay. So next is your MPUs. So in the MPUs, it is employing a simple system. So where you are going to have the limited production here. So your MPU, the memory with limited memory production unit. So this particular memory production unit is going to provide you the limited production. So when you are going to have the limited production, so where this particular type of memory is used. So in this since it is providing the simple limiting the production. So it employs a simple system used for systems that require memory protection that doesn't have the complex memory map. That means complex memory map means what? The more number of events are going to occur with respect to your embedded system. So more decisions has to take place. More depending upon the more decisions what it is going to take place. Different more countermeasures has to be taken place. So when you are going to have the this embedded system, which one is complex, there in this one, you cannot use your memory production unit since the memory production unit is going to have the limited production. Okay, so your memory production unit is going to have the limited production. So next, so this where these regions are controlled. So when you are going to have the the don't have the complex memory map. So where you are going to have how it is going to used. So how this particular memory map is going to be used since it is going to have the immediate protection. So these regions are controlled with a set of special coprocessors. Okay. So even if you take the memory management unit, so even the memory management will be unit which is designed to more sophisticated operating systems that support multitasking. So your MMUs are used when you want to have more number of events to be occurred, and where your embedded system should have more multitasking. So when I am telling that when you are having the embedded system, inside the embedded system, what you have to run, any hardware if you take, if it has to run, who is acting as an interface between the user and the hardware? Your operating system. When your operating system is acting as a interface between the user and the hardware, what it is going to have? So it is going to have some management technique, how to manage the file, how to give the security for the system, how I have to increase the speed. So these things has to be taken care by your processor with respect to the hardware. Okay. So when you are going to connect you, and this will be this type of environment is basically used for systems that require memory protection. Okay. So that is where it is going to use. The last one is your memory management unit. So this is a complex or comprehensive memory management hardware. So your memory management unit is nothing but a complex or comprehensive memory management hardware available in ARM. Available in ARM. So what this particular memory management unit, which is stored in your ARM, is going to provide. So whatever the translation table you're going to have, it uses a set of translation table. So if you have the translation table, what it is going to provide, it is going to provide you the fine-grained control over memory. So it is basically providing the fine-grained control over memory. So where this particular table is located first. So these tables are located in main memory. Okay, this particular these particular tables are located in memory, and it is going to provide you the virtual to physical address. Okay, so this virtual, how it will be generated from virtual to physical address or physical to virtual address, that you are going to study in your operating system, that you come to know. So these tables are more are stored in memory, and it is going to provide you the virtual to physical map address. Okay, and apart from your mapping the virtual to physical address, so that means when you are accessing it, your cache memory will be not having the exact address, right? First it has to fetch the data from the main memory. In the main memory, some for at some address, that some data will be there, but the say maybe in the 10th address your instruction has to run, but in the cache you are going to have the address starting from 0, but it has to map the physical address. The 10th address which is there in my memory has to be stored in the 0th address of the cache. That is what it is called as address mapping, that is virtual to physical address mapping. Okay, so that you will understand when you are operating in the operating system cache, operating system subject itself, that you are going to in detail you are going to study in your operating system. So it is going to be designed in more sophisticated operating system environment, and it is going to have the multitasking capability. So your memory management unit which you are going to have, they are designed for more sophisticated platform operating system that supports multitasking. So that is where you are going to make use of the MMUs. So by using what it is going to do the multitasking, since it is having the translation tables, so which will provide you the fine grained control over memory. So fine grained control is one thing, but what with a limited support, it is going to control the memory. That is called as fine grained. Coarse grained means what? I have all the components required to run the particular application. With all the components, it is going to control the memory. That is coarse grain. So when you are going to have that grains, so you are going to have two different types of grains. So just for your knowledge purpose, I am telling one is fine grain, other is coarse grain. So fine grain is what? Limited set of functionalities will be there, or function units will be there. Limited set of function units will be performing the operation. If you are going to have the coarse grain, it is going to have the more function units. So that's what the statement tells between the fine grained fine grained control over memory, or if you talking about the difference between the fine grain and coarse grain. Coarse grain is nothing but what? It's going to have the more functional units, and with the help of those functional units, it's going to control over the memory. So this is how the memory management unit. So there are three types in your memory management. One is no core extension, right? So it doesn't give any production, no extensions. Second is memory production unit. So it is going to provide you the limited production. Third is the memory management unit. So it is going to provide you the fully protected system. So that is going to provide you the full protection for your processor. Okay. So the last topic is your processor core. So what do you mean by coprocessor? So next is we have discussed about three. One is tightly cache, tightly coupled memory, memory management unit, and coprocessor interface. So the last topic in your first module is coprocessor. So how that particular coprocessor can be attached to the ARM processor. So first you should know that how the coprocessors can be attached to the ARM processor. So now how it will be extended. So a coprocessor is going to extend the processing feature of the core by extending the ARM instruction set. Okay, by extending the instruction set or by providing the configuration registers. So you're going to have the configuration registers. So depending upon the configuration registers, it is your coprocessor will be attached to the ARM core, and it is going to map. This particular register is going to be having in ARM, and another set of registers will be there in the another processor which is been attached to the main ARM processor. So it has to extend the instruction set. That means what? With the help with the instruction set which is supported by your ARM processor, along with those instruction set, the instruction set which is supported by the other processor which is attached. That instruction set is also be attached here, because some set of features will not be supported by the ARM core. When some set of features are not supported by the ARM core, what I am doing, I am attaching another processor which will support my embedded system. And when you are attaching that particular processor to your ARM core, those instructions which are not executed by the ARM will be executed by your coprocessor. You understood? So that is why you are going to attach with the coprocessor. So what it will extend, what's the functionality it is going to provide you? The coprocessor is going to extend the processing features of a core. So a coprocessor which you are going to have, it is going to extend the processing features of a core by extending what? By extending the instruction set or by providing the registers. It is nothing but what? So you can increase the instruction set if you have the additional processor. So now if you take the ARM processor, it is going to have 16 general purpose register and 2 status register, right? So you are in the 2 general purpose registers, 16 general purpose register, 3 are specifically used for stack pointer, link register, and program counter. So those 3 registers I cannot use. I cannot make use. I can use only the other 13 registers. Okay. So along with those 13 register, if other coprocessor which you are attaching, if it is having another 8 register, assume that my another coprocessor is having 8 register. Now your program can utilize that 13 register plus 8 register. So now your program can utilize 21 registers, different registers. So when you are using more number of registers, obviously the dependencies which are there to execute the instructions will become less. So your performance of the systems will be improved. Okay. So if we take the coprocessor, so it can be your coprocessor, how it can be accessed? It can be accessed through a group of dedicated ARM instruction that provided load store type interface. Okay, so coprocessor can be accessed through the group of instructions which is supported by ARM, which will provide you the load store type interface. That means when you talk about the load, so what it will do, the load will going to access the data which is stored in the memory to the register. Similarly, here what will happen if you want to access the coprocessor? So what it should have? It should have some dedicated instruction. ARM instruction should be there. So if you issue that particular ARM instruction, what it will do? So it will access the coprocessor. Those instruction is going to access the coprocessor through the coprocessor interface. Okay, and it will be added into your processor, and it will be seamlessly working with the processor as though as single processor is working. Okay, so when you are accessing it through a take the coprocessor 15 is there, some of the examples which you can take. So it is going to have the ARM processor uses coprocessor 15 registers to control the cache, tightly coupled memory and memory management. Okay, so your coprocessor, if you take, it can also be extended the instruction set by providing a special group of new instructions. So that is nothing but what? So I have another processor, it will be having some set of instruction set. Okay, so my ARM is having some set of instruction set. So when you attach the coprocessor, what will be having? I'm extending the instruction set. Okay, what do you mean by extending the instruction set? It is nothing but assume that your ARM is having 15 instruction, and assume that your coprocessor is having around 15 instruction. But whatever the instruction supported by your ARM processor will not be supported by your coprocessor. That's what I am at. That is why I am attaching the coprocessor into the ARM core, because I want that particular features to be inserted into your embedded system. Now, along with the instructions which is run by your ARM, your another instructions which is controlled by your coprocessor will be also added. So that means it is going to increase the number of instructions, or it is going to be increasing the group of new instructions are added into your embedded system. So now, where this particular new instructions are to be accessed or processed, if you take the stage pipelining, so where the instructions are started with what to perform in this state, if you take the pipelining, in which stage your pipeline your processor decides that what operation it has to perform in which stage. Any answers from your side? For example, if you have the 3-stage pipelining, one is your fetch, decode, execute. In which stage your ARM processor is going to decide what operation to be performed, whether it's in a fetch stage, or whether it is in a decode stage, or whether it is in a execution stage. Which stage? It's basically in the decode stage. So here also, whatever the new instructions it is supported by your coprocessor is going to be processed in the decode stage of the ARM pipeline. Okay. So whatever the new instructions which you are going to have in your coprocessor, those new instructions are processed in the decode stage of the pipelining. Okay. So now, if the decode stage sees a coprocessor instruction, what it has, so it offers it to the relevant processor. So if it is a decode state, what will happen? I am told that you have to access the coprocessor using the dedicated ARM instruction, right? So when you are going to have the ARM dedicated instruction to access the ARM core, so at the decode stage, if it sees that particular instruction which it is running is a coprocessor instruction, so it offers to whom? Then it offers to the relevant coprocessor. So now if that particular coprocessor is not present, and if that it doesn't have the recognizing the instruction, so now what type of execution it what type of exception it is going to take? Since yesterday we have decided that discussed that you have a different type of exceptions, right? So in that one, when you are going to have, when you are if in the decode stage, for example, so if the instruction which has to be executed is a coprocessor instruction, so then it give control to the coprocessor. Okay. Now, for example, I issue the coprocessor instruction, but I have not connected any coprocessor to your embedded system or ARM. So then, what type of exception it is going to execute at the time? Anybody is having an answer? I have done it yesterday. You have to tell. So there are different type of exceptions you are going to have. So first one is reset, undefined instruction, software interrupt, prefetch abort, data abort, reserved, interrupt request, and fast interrupt request. Now, whenever the processor is not able to decode an instruction, what type of interrupt it is going to occur? Whenever your processor is not able to decode the instruction, it will be generating the undefined instruction. Okay. So whenever your ARM processor is going to execute the instruction which has to be accessed from the coprocessor, if it is a coprocessor instruction, then next, and if the coprocessor is not present, you have to keep it in mind that if the coprocessor is not present, then ARM takes an interrupt called as undefined instruction execution. So now what it does, it allows to emulate the behavior of the coprocessor in software. So whatever the software you are going to have, so that it is going to emulate the behavior of the coprocessor in the hardware. Okay. So any doubt till now? So that completes your module 1. Anybody is having any doubt? So from next class, we will start with the ARM instructions. So it will be helpful for your programming also. So it will be very interesting for you people. So we should have the basics of your registers there. Anybody is having any doubt? So what are the things you have to read here is, first you have to go through the RISC design philosophy. So RISC design, what are the different stages for philosophy design rules it is going to follow. So next you have to go with ARM design philosophy, and what is the instruction set for your embedded system. So we discussed about your embedded system hardware and what are the different bus technologies which you are going to have. So next you're going to have the memory concepts. So you are going to have, we are discussed about your embedded system hardware and embedded system software. After discussing your embedded system hardware and embedded system software, we gone with the ARM core data flow models. So you should know how the flow of the data is going to occur. So next we discussed about the registers and the banked register. After discussing with respect to the registers and the bank registers, we are going to discuss with the CPSR, that is current program status register, and different mode of operation. Okay, so if you are aware, what are the different processor modes your ARM is going to work. So next, the last one is your exceptions. We discussed about the interrupt vector table. After discussing the interrupt vector table, we discussed about the condition flags, that is the fields with respect to your current program status register. Okay. So there are four fields which you are going to have in your CPSR. What are the different four fields? That is your flags, status, extension, and control. Okay. Once you have this one, we discussed about the conditional execution. So last, pipelining, it is also important for your examination point of view. So apart from the part exceptions, vector table, and interrupts, the last one is your core extensions. So in the core extensions, you are going to have four. So that is nothing but your cache, tightly coupled memory, cache and tightly coupled memory, and you are going to have the memory management unit and coprocessor. So these are the three things which you should have. So anybody is having any doubt? So whatever the assignment questions have been given, you start writing the assignment questions so that it will be useful for your test also, IA also. So those are the questions which I am going to give for your IA. So it will cover the entire syllabus of your first module. Anybody is having any doubt with respect to the first module? Anybody having any doubt? So if you have any doubt, you can ask now. Anybody having any doubt?